Criteria of purity. We have been learning about mixtures. However, some substances are not mixtures. They occur as pure substances. In this subtopic, we are going to learn the method that we can use to identify whether a substance is pure or not. Let us begin with investigating what happens when pure ice is heated to steam. You need to set up the apparatus as shown in this diagram, whereby you will heat some crushed ice in a beaker and you put a thermometer in the ice to record the temperature change as time goes by. Then you fill in the temperature at intervals of 30 seconds from the time you start heating. The melting point of water or ice is 0 degrees Celsius at sea level, while the boiling point of water is 100 degrees Celsius. Now, after carrying out this experiment and recording the different temperatures at half-a-minute intervals, we'll obtain a curve or a graph. The heating curve obtained when heating pure ice to steam is shown below. At region AB, the temperature rises steadily as the ice particles gain kinetic energy. And begin to vibrate more vigorously. In fixed positions. At region BC, the temperature remains constant, while the heat supplied is used to weaken the forces of attraction between the particles, and therefore the solid turns into a liquid. In region CD, the temperature rises steadily as the liquid particles gain kinetic energy and begin to move more vigorously. By the time the temperature reaches point D, we'll get to point DE, where the temperature remains constant and the heat supplied is used to break the bonds between the liquid particles, and therefore the liquid boils. That means it turns from a liquid into a gas. Then we move to region EF, where now we have the gaseous state. So the gas particles, as heating continues, the temperature rises steadily. The gas particles gain more kinetic energy and move more vigorously in random motion. As a summary of what we have just described, this diagram explains that at region B, the solid will start to melt, and by the time we get to region C, at point C, the melting is complete, and now we have a liquid. The temperature rises until point D, where the liquid starts to boil, and by point E, the liquid has completely boiled and formed a gas. In this next setup, we investigate what happens when pure naphthalene is heated. Now, the melting point of naphthalene is about 80.2 degrees Celsius. When we heat naphthalene in a water bath, as shown in this diagram, and record our temperature at intervals of half a minute throughout the experiment, we will obtain a curve or a graph as shown in the next slide. The heating curve obtained when naphthalene is heated is shown in the diagram below. Point AB, or region AB, naphthalene particles gain heat energy and begin to vibrate more vigorously in fixed positions as the temperature rises. By the time we get to point B, naphthalene begins to melt and the temperature remains constant. The heat energy provided is used to weaken the forces of attraction between naphthalene particles, and therefore it begins to melt. By point C, all of it has melted, and now we have liquid naphthalene. The temperature again begins to rise steadily as the particles absorb heat energy and begin to move vigorously. This type of curve is known as the heating curve of naphthalene. We cannot obtain the temperature, the boiling point of naphthalene, using the Bunsen burner in the laboratory. That is why this diagram, the heating curve, only ends at point D, and it cannot continue to show the other details.